Tonight, we journey to the birth of the sun. You have nothing to do but rest. Let your breathing slow, let your thoughts grow quiet, and let the cosmos carry you gently to sleep. There is no hurry tonight, no task, no deadline, no alarm waiting at the end of this journey. You are exactly where you need to be, resting, breathing, letting the world outside do whatever it does, while you stay here, warm and still and safe. If you are lying down, let the full weight of your body settle into whatever is beneath you. Let the mattress or the pillow or the floor receive all of you, every kilogram, every ounce of tension, every thought that has been circling your mind today. You can set all of it down now, the way you would set a heavy coat on a hook beside the door, and walk away from it, knowing it will be there in the morning if you need it. But tonight, you do not need it. Let your jaw unclench. Let the muscles around your eyes go soft. Let the space between your eyebrows become smooth and wide, as though someone very gentle has pressed a warm cloth there, and all the tightness has dissolved. Your shoulders can lower just a little, not all at once, just enough to notice, as though the weight of the day is sliding off the edges of you, down through the bed and into the floor beneath. Your hands can open, your fingers can uncurl, your wrists can go soft, and your breathing, you do not need to control it, just notice it, in and out, in and out. Each breath a little slower than the last, each exhale a little longer, a little more complete, like a tide pulling gently back from the shore, leaving the sand smooth and quiet. The room is still around you. The air barely moves. Whatever sounds exist beyond these walls can stay out there. They do not belong here. Here there is only the quiet and the story. And tonight's story is one of the most beautiful stories in all of science. It is the story of how our star was born. Not a distant star, not a star in another galaxy, but our star, the sun. The same sun that warmed your face this morning or yesterday morning or the morning before. The same sun that has warmed every face of every person who has ever lived on this small blue planet. 4.5 billion years ago, in an ordinary corner of the Milky Way, there was no sun, there was no Earth, no moon, no Mars, no Jupiter, no ocean, no sky, no air. There was only a vast, cold, dark cloud of gas and dust, drifting silently through the galaxy, with no particular destination and no particular hurry. This is where our story begins, in the dark, in the cold, in the quiet, in a place where nothing seemed to be happening, and yet everything was about to begin. In and out. The bed holds you. You are safe and still, and the universe is ancient and patient, and the story it is about to tell you has been waiting 4.6 billion years for this exact moment. To understand the birth of the sun, you need to understand where stars come from, and the answer is both simple and beautiful. Stars come from clouds, not the soft white clouds you see in a summer sky, but enormous clouds of gas and dust that drift through the spaces between stars, filling the galaxy like mist filling a valley. These are called molecular clouds, and they are among the largest structures in the Milky Way. Some of them are hundreds of light years across, so vast that light itself, the fastest thing in the universe, takes centuries to cross from one side to the other. They are made almost entirely of hydrogen, the simplest element, the lightest element, the element that has existed since the universe was just a few minutes old. Hydrogen atoms, each one nothing more than a single proton circled by a single electron, drifting through the dark in their trillions upon trillions upon trillions. Mixed in with the hydrogen is a smaller amount of helium, the second simplest element, also forged in the first few minutes after the Big Bang. And scattered throughout the cloud like pepper through salt, tiny grains of dust, microscopic particles of silicon and carbon and iron and oxygen, the ashes of stars that lived and died long before our sun was even a possibility. These dust grains are ancient. They carry the memory of supernovae that exploded billions of years earlier, stars that burned through their fuel and scattered their heavy elements across the galaxy, seeding the interstellar medium with the raw materials for new worlds. The cloud that would become our sun, our solar system, everything you have ever known or touched or stood upon, was made of this recycled stardust. It was not fresh material. It was material that had already been inside at least one star, and probably several. You are made of second-hand atoms, and there is nothing second-rate about that. It means your atoms have a history, a biography that stretches back to the earliest generations of stars in the Milky Way. The room is warm around you. The air is gentle against your skin, and every atom of that air was once part of the same cloud that gave birth to the sun. The nitrogen you breathe was cooked inside a star. The oxygen was forged in a stellar furnace. The carbon in your body passed through a supernova. You are breathing stardust right now as you rest. In and out. The molecular cloud that would become our solar system drifted through the galaxy for millions of years, cold and dark and patient. It had a temperature of only about 10 to 20 degrees above absolute zero, roughly minus 250 degrees Celsius, colder than anything you will ever experience, colder than the surface of Pluto, colder than the space between the planets. At that temperature, the hydrogen molecules moved very slowly, barely vibrating, barely bumping into each other. The cloud was incredibly still, like a frozen fog hanging in the emptiness of space. And it was dark. The dust grains scattered throughout the cloud blocked nearly all the starlight from passing through. If you could have stood inside this cloud, which you could not, because there was no air and no warmth and no ground to stand on, you would have seen almost nothing, a deep, impenetrable, ancient darkness. Not a frightening darkness, not an aggressive darkness, but a quiet one, a still one, a darkness that felt like rest, like the pause between one breath and the next, like the moment just before sleep takes hold. The kind of darkness you might be feeling now, behind your closed eyelids. The kind of darkness that holds you rather than hides from you. Inside this dark cloud, gravity was at work, very gently, very patiently. Gravity is the weakest of the four fundamental forces in nature, far weaker than the electromagnetic force that holds atoms together, far weaker than the strong nuclear force that binds protons and neutrons in the nucleus, far weaker than the weak nuclear force that governs radioactive decay. But gravity has one extraordinary advantage over all the other forces. It never stops. It has infinite range. Every particle of mass in the universe pulls on every other particle of mass, no matter how far apart they are. The pull may be vanishingly small across cosmic distances, but it is never zero. It is always there, patient and persistent and tireless. And in a cloud of gas and dust that has been drifting for millions of years, even the gentlest pull of gravity can accumulate into something significant. Inside the molecular cloud, denser regions formed, places where the gas happened to be slightly thicker than its surroundings, just by chance, just by the random jostling of molecules. These denser regions had slightly more mass, and therefore slightly more gravity, and that extra gravity pulled in a little more gas from the surrounding cloud, which increased the mass further, which increased the gravity further, which pulled in even more gas. A slow, quiet, self-reinforcing cycle, a gathering, a drawing inward, like the way sleep draws you inward, each moment of relaxation making the next moment of relaxation easier, each breath pulling you a little deeper into rest, in and out. Let that drawing inward happen to you now. Let gravity do its work, pulling you gently down into the mattress, down into the pillow, down into the warm, dark quiet of sleep. But the cloud was not ready to collapse. Not yet. Something was missing. The dense regions inside the cloud were in a kind of balance. The inward pull of gravity was matched by the outward pressure of the gas molecules bouncing off each other, even at those frigid temperatures. The cloud needed a nudge, a push, a whisper from outside. And that whisper came from the most violent event in the cosmos. Somewhere nearby, in cosmic terms, a massive star died. We do not know exactly which star it was, or precisely where it was, or exactly when the explosion happened. But the evidence is written in the atoms of our solar system, in the isotopes of elements like aluminium-26 and iron-60 that could only have been produced in a supernova, and that must have been present in the cloud at the time of its collapse. A supernova, the death of a star more than 8 times the mass of our Sun, an explosion so powerful that for a few weeks it outshines an entire galaxy of hundreds of billions of stars. When a massive star explodes, it sends a shock wave outward through space at thousands of kilometers per second, a wall of compressed gas and radiation that expands in all directions like a ripple spreading across a pond. This shock wave would have reached our molecular cloud, and when it hit, it would have compressed the gas, squeezing it, pushing the denser regions past the tipping point where gravity could overcome pressure. Imagine a row of dominoes, standing upright, perfectly balanced. Each one is stable on its own, but if you give the first one a gentle push, they all fall, one after another, in a cascade that cannot be stopped once it begins. The supernova shockwave was that gentle push. It compressed the densest part of the cloud just enough to trigger what astronomers call gravitational collapse. The moment when gravity takes over, when the inward pull becomes stronger than any outward pressure, and the cloud begins to fall inward upon itself. This is the moment our solar system was conceived. Not with a bang, not with a flash, but with a gentle compression, a quiet tipping point, a whisper from a dying star saying to the cloud, "It is time, you can begin now." The bed holds you. The room is dark and still, and 4.6 billion years ago, in a cloud of cold gas and ancient dust, something extraordinary began. A gathering, a pulling inward, a slow collapse that would eventually produce the sun, the earth, the oceans, the air, and you. In and out. Let us linger a while in the molecular cloud before the collapse has truly taken hold, because there is so much beauty in the quiet that came before. The cloud from which our sun was born was not alone. It was part of a much larger structure, a giant molecular cloud complex, perhaps 1,000 light years across, containing enough gas to make tens of thousands of stars. Within this larger cloud, there were pockets of density, regions where the gas was thicker, cooler, more compressed. These are called dense cores, and each one was a potential star, a seed waiting for the right conditions to begin growing. Our sun's dense core was one of perhaps hundreds or thousands in this region of the cloud, all of them at various stages of readiness, some already collapsing, some still waiting, some that would never collapse at all, that would simply drift and disperse over millions of years without ever producing a star. There is something humbling about that. Our sun was not destined to exist. It was not inevitable. It was one possibility among many, one seed that happened to receive the right nudge at the right time. If the supernova shockwave had arrived a little earlier or a little later, if the dense core had been a little less dense or a little more, if any of 1,000 random factors had been slightly different, our sun might never have formed, and neither would the Earth, and neither would you. But they were not different. They were exactly what they were. And here you are, lying in a warm bed on a planet that orbits a star that almost did not exist, breathing air that was once cold hydrogen in an ancient cloud. The room is quiet, the world is settled. You are one of the universe's most improbable creations, and you are resting in and out. Inside the dense core, before the collapse, the temperature was extraordinarily low, roughly 10 degrees above absolute zero, which is minus 263 degrees Celsius. At that temperature, the hydrogen molecules drifted through the cloud at a speed of only a few hundred meters per second, which sounds fast by human standards, but is incredibly slow for gas molecules. In the air you are breathing right now, the nitrogen and oxygen molecules are moving at about 500 meters per second, nearly twice as fast. The cold gas moved slowly, quietly, barely interacting with its neighbors, each molecule drifting through the dark like a tiny ghost, alone, patient, waiting. And the dust grains, those tiny particles of silicon and carbon and iron, they were even more still. They drifted with the gas, carried along by gentle currents, each one coated in a thin layer of frozen molecules: water ice, carbon dioxide ice, methane ice, ammonia ice, a tiny frozen world on the surface of each microscopic grain. Some of these icy dust grains would eventually become part of comets. Those frozen coatings of water and carbon dioxide would be preserved for billions of years, locked inside chunks of ice and rock at the outer edges of the solar system, carrying the original chemistry of the molecular cloud across the entire lifespan of the sun. When you see a comet in the night sky, with its bright head and long glowing tail, you are seeing material from the original molecular cloud, material that has been frozen in storage for 4.6 billion years, now thawing in the warmth of the sun for perhaps the first time. Comets are messengers from the birth of the solar system, carrying the memory of the cloud in their ice. Let your eyelids feel heavy, let your muscles soften. The universe remembers everything, and you can forget everything, at least for tonight. The memories will keep the way the ice in a comet keeps, frozen and safe, until you need them again. In and out. The chemistry of the molecular cloud was surprisingly complex. Even at those frigid temperatures, reactions were happening slowly on the surfaces of the dust grains, where atoms and molecules could meet and bond without the thermal energy to break them apart again. Water formed this way, an oxygen atom landing on a dust grain, encountering a hydrogen atom already stuck to the surface, bonding together, then finding another hydrogen atom and forming a molecule of water, H2O, the most important molecule for life as we know it. Methanol formed, formaldehyde formed, amino acids, the building blocks of proteins, may have formed on these grain surfaces too. The chemistry of life was beginning, not in a warm pond on a young planet, but in the frozen dark of an interstellar cloud, billions of years before the first planet even existed. The seeds of biology were being planted in the nursery of astronomy, and neither knew the other was there. This is one of the most extraordinary things about the story of the sun. It is not only the story of a star, it is the story of everything that star would eventually make possible: planets, oceans, atmospheres, chemistry, biology, consciousness, thought, wonder, rest. All of it encoded in the atoms and molecules of a cold, dark cloud, waiting for gravity to say, "Begin." The bed holds you, the room is warm, and the chemistry that makes you possible has been unfolding for 4.6 billion years and will continue for billions more, patient and intricate and beautiful beyond all description. In and out. Now let us return to the moment of the supernova, that distant dying star whose shockwave whispered to our cloud, and understand what that whisper truly meant. When a massive star explodes as a supernova, it does more than produce a shockwave. It also scatters freshly forged elements into the surrounding space, elements that were created in the star's core during its life, and elements that were created in the supernova explosion itself. Among those elements were radioactive isotopes, atoms with unstable nuclei that decay over time, releasing energy as they transform into more stable forms. One of the most important of these was aluminium-26, a radioactive form of aluminium with a half-life of about 717,000 years, meaning that half of any given sample will have decayed after that time. Aluminium-26 has been found in ancient meteorites, in the oldest rocks in our solar system, in tiny mineral grains called calcium-aluminium-rich inclusions that formed in the first few million years of the solar system's existence. The presence of aluminium-26 in these ancient grains tells us something crucial. It tells us that a supernova must have occurred nearby, and recently, injecting freshly made radioactive aluminium into the cloud just before or during its collapse. If the supernova had happened too long before the collapse, the aluminium-26 would have decayed away before it could be incorporated into the first solid objects in the solar system. Its presence means the timing was close, within a few 100,000 years, possibly less. The supernova did not merely trigger the collapse of our cloud, it also enriched it. It added fresh elements to the mix, elements that would play crucial roles in the formation and early heating of the planets. The radioactive decay of aluminium-26 and other short-lived isotopes generated heat inside the earliest planetesimals, the small rocky bodies that formed in the protoplanetary disk. This heat was enough to melt the interiors of some of these bodies, allowing heavier elements like iron to sink to their centers and lighter materials to rise to their surfaces. This process, called differentiation, is why the Earth has a dense iron core surrounded by a lighter rocky mantle. It happened because a dying star gave our cloud radioactive elements that generated heat inside the first solid objects, shaping their internal structure before any of the planets had fully formed. The structure of the Earth you are lying on right now, the iron core thousands of kilometers below your bed, the rocky mantle beneath the surface, was determined by the gift of a dying star, a supernova that exploded 4.6 billion years ago and seeded our cloud with the radioactive warmth that melted and sorted the earliest rocks. Your body rests on layers of rock that were shaped by a star that died before the sun was born, and that is remarkable. In and out, the story builds, layer by layer, The way the Earth was built, layer by layer, patient and slow and irrevocable. Once the collapse began, it could not be stopped. Gravity had won the argument, and now it would take its time, pulling the cloud inward, atom by atom, molecule by molecule, grain of dust by grain of dust. But the collapse was not fast, not by human standards. It took roughly 100,000 years for the cloud to shrink from its original size, many light years across, down to something resembling the beginnings of a solar system. 100,000 years. That sounds like a very long time, and by the measure of a human life, it is. But in cosmic terms, it is a blink. The universe was already 9.2 billion years old when this collapse began. 100,000 years is less than 1/1,000,000th of that age, a brief, quiet gathering. As the cloud collapsed, something beautiful happened, something dictated by one of the simplest laws in all of physics. It began to spin. The original cloud was not perfectly still. It had a tiny, barely detectable amount of rotation, just the faintest hint of spin, inherited from the random motions of the gas within the larger molecular cloud. But as the cloud shrank, that tiny rotation amplified enormously. This is because of something called the conservation of angular momentum, and you already understand it intuitively, even if you have never heard the name. Think of a figure skater. When a skater spins with their arms stretched wide, they rotate slowly, but when they pull their arms in close to their body, they spin much faster. Their total angular momentum stays the same, but because the mass is closer to the center, the speed of rotation increases. The collapsing cloud was like that skater pulling their arms in. As the gas fell inward toward the center, it spun faster and faster. The gentle, almost imperceptible rotation of the original cloud became a vigorous swirl, a cosmic whirlpool, turning and gathering speed. The room is still, your body is still, but 4.6 billion years ago, the cloud that would become everything you know was spinning, gathering, falling inward like water spiraling down a drain, but in reverse, not emptying but filling, concentrating, building toward something extraordinary. In and out, let the image of that spinning cloud be gentle in your mind, not urgent, not dramatic, just a slow, quiet swirl, like cream turning lazily in a cup of tea. As the cloud spun faster, the shape of the collapsing material began to change. Originally it was roughly spherical, a lumpy, irregular ball of gas and dust, but the spinning introduced a new force, centrifugal force, the tendency of rotating material to fly outward from the axis of rotation. Along the axis of rotation, there was no centrifugal force, so gas fell freely inward, collapsing quickly in the direction of the poles. But perpendicular to the axis, in the plane of rotation, centrifugal force resisted the collapse. Material in the equatorial plane could not fall all the way to the center. It was held in orbit, spinning around and around, supported by its own rotation. The result was that the sphere flattened. The poles collapsed inward while the equator stayed wide, and the cloud transformed from a ball into a disk. This is the protoplanetary disk, and it is one of the most important structures in the story of our solar system. Picture it, a vast flat disk of gas and dust, hundreds of astronomical units across, slowly rotating, with a dense hot bulge at its center where most of the mass has collected. This central bulge is the protostar, the infant sun, not yet a star, not yet burning, but growing, warming, compressing, preparing for the moment when it will finally ignite. The disk itself was not uniform. It was thicker near the center and thinner at the edges. It was hotter near the protostar and cooler farther out. It was dense enough in places to be opaque, blocking light from passing through, and thin enough in other places to be nearly transparent. If you could have seen it from above, it would have looked something like the rings of Saturn, but far larger, far more massive, and far more dynamic, a swirling disk of gas and dust and tiny particles of ice and rock, all orbiting the growing protostar at its heart. And within this disk, the seeds of every planet in our solar system were already present, the materials that would one day become Mercury and Venus and Earth and Mars and Jupiter and Saturn and Uranus and Neptune. All of it was there, mixed together in the disk, waiting to be sorted and assembled by gravity and chemistry and time. The blanket holds your warmth, the pillow cradles your head. You are resting in a room on a planet that was once dust in a spinning disk, orbiting a star that did not yet exist 4.6 billion years ago. Everything you have ever known was once part of that disk. Every mountain, every ocean, every grain of sand on every beach, every bone in your body, every breath you have ever taken, all of it was there, swirling slowly around a growing ball of hot gas, waiting to become something, in and out. At the center of the disk, the protostar was growing. As more and more gas fell inward from the surrounding cloud and disk, the protostar's mass increased, and with it, its gravity, its temperature, and its density. When gas is compressed, it heats up. This is a simple fact of physics that you experience every time you pump air into a bicycle tire. The act of compression transfers energy to the gas molecules, making them move faster, and faster moving molecules mean higher temperature. The protostar was being compressed by an enormous amount of gas falling onto it from all directions, and the temperature at its core was rising steadily, 10,000 degrees, 100,000 degrees, 1,000,000 degrees. At each stage, the protostar glowed brighter, not yet with the light of nuclear fusion, but with the heat of gravitational compression, the energy of billions of tons of gas falling inward every second, converting their gravitational potential energy into thermal energy as they crashed into the growing protostellar core. This is called the Kelvin-Helmholtz mechanism, named after two 19th century physicists who first calculated how much energy a contracting ball of gas could produce. Before nuclear fusion was understood, scientists believed this was the source of the sun's energy, and they were partly right. It is the source of a protostar's energy during the millions of years before fusion begins. The young protostar was hot, and getting hotter, it glowed with infrared light, invisible to the human eye but detectable by the right instruments, a warm presence in the center of the disk, like a hearth in the center of a cold room, radiating warmth outward into the surrounding gas and dust. The room you are in is warm too, perhaps from a heater, perhaps from the residual warmth of the day, perhaps from your own body heat, radiating gently into the air around you. You are your own small protostar, a warm center in a cool room, and the physics is the same. Energy flows from hot to cold, from concentrated to spread out, from you into the world, in and out. The protostar continued to grow for roughly 100,000 years, pulling in gas from the surrounding cloud at a prodigious rate, sometimes as much as 1/1,000,000th of a solar mass per year, which sounds small until you realize that 1/1,000,000th of the sun's mass is still about 2 times 10 to the power of 24 kilograms, roughly the mass of the Earth every 3 years. The protostar was eating voraciously, growing larger and hotter with every passing century. And as it grew, the disk around it evolved too. Gas and dust continued to fall inward from the outer edges of the cloud, spiraling through the disk, losing energy through friction and turbulence, and eventually accreting onto the protostar. The disk was not a calm place. It was turbulent, dynamic, full of eddies and currents and shock waves as gas streams collided and interacted. But from a distance, from above, it would have looked serene, a slow, graceful swirl of material, like the spiral arms of a galaxy in miniature, turning and turning and turning. Let that image settle in your mind, a vast spinning disk, warm at the center, cool at the edges, with a growing ball of fire at its heart, turning slowly in the dark. The first structure our solar system ever had, the first shape our corner of the universe ever wore. In and out, the disk turns, and you rest, and the universe is patient. Let us now follow the collapse more closely, step by step, the way you would follow a path through a forest, slowly, noticing everything. In the very first phase of the collapse, which astronomers call the isothermal phase, the cloud fell inward freely, and remarkably, it did not get much hotter. This seems strange, because we said earlier that compression heats gas, and that is true. But in the earliest stages, the cloud was so thin and so transparent to infrared radiation that any heat generated by the compression was immediately radiated away into space. The gas compressed, heated up a little, radiated that heat away, and stayed cool, falling inward at roughly the speed of sound in the cloud, about 200 meters per second. This free-fall phase lasted for several tens of thousands of years, and during this time, the cloud shrank enormously, from a size of many billions of kilometers down to something much more compact. The density at the center increased by many orders of magnitude, while the temperature stayed nearly constant. But eventually, the center became so dense that it could no longer radiate its heat away efficiently. The gas became opaque to infrared light, trapping the energy inside, and for the first time, the temperature at the core began to rise significantly. This is the moment when the protostar was truly born, a hot, dense core of gas no longer able to cool itself, growing hotter and hotter as more material continued to rain down upon it from the surrounding cloud. The blanket is warm around you, and 4.6 billion years ago, a ball of gas in the center of a collapsing cloud was becoming warm too, for the first time, trapping its heat the way your blanket traps yours, holding the warmth close, letting it build, in and out. The growing protostar quickly reached a new kind of balance, a temporary equilibrium between the heat being generated by compression and the energy being radiated from its surface. This is called hydrostatic equilibrium, and it is one of the most important concepts in all of stellar physics. Think of it this way. The gas at the center of the protostar is being squeezed by the weight of all the gas above it. This creates enormous pressure, trying to crush the core down to nothing. But the hot gas at the core is also pushing outward, its thermal energy creating pressure that resists the compression. When these two forces are in balance, when the inward pull of gravity is exactly matched by the outward push of gas pressure, the protostar is in hydrostatic equilibrium, a perfect balance, where the sun's inner fire pushes out just enough to hold back the crushing weight of all the material above it. It is the same balance that keeps the sun stable today. 4.6 billion years later, gravity pulling inward, pressure pushing outward, and the two meeting in the middle, holding the sun in a state of almost perfect equilibrium for billions of years. You might be in a kind of equilibrium too right now, the weight of your body pressing down, the mattress pushing up, the pull of sleep drawing you inward, the faint thread of wakefulness holding you at the surface, a balance, temporary and gentle, that will eventually tip, as all balances do, in the direction of rest. In and out. The protostar was now a distinct object, separate from the rest of the cloud. It had a surface of sorts, where the infalling gas struck the protostellar material and released its kinetic energy as heat and light. This boundary layer was extremely hot, glowing brightly in infrared. But you could not have seen it with your eyes. The protostar was still buried deep inside the remnants of the molecular cloud, surrounded by a thick envelope of gas and dust that absorbed all the visible light and re-radiated it at much longer wavelengths. From outside, the collapsing cloud would have appeared as a dark silhouette against the background stars, a shadow in the galaxy, with no hint of the growing fire at its heart. Astronomers today can see objects like this in nearby molecular clouds. They are called Class 0 protostars, and they are visible only in far infrared and radio wavelengths using telescopes that can see heat rather than light. The Atacama Large Millimeter Array, ALMA, a collection of 66 radio telescopes in the Chilean desert, has photographed dozens of protoplanetary disks around young stars, revealing the swirling structures with astonishing clarity, showing rings and gaps and spiral patterns that tell the story of planet formation in action. When astronomers look at these young disks around other stars, they are seeing what our solar system looked like 4.6 billion years ago, before any of the planets had formed, before the sun had ignited, before the story had truly begun. It is like finding a photograph of yourself as an infant, before you could walk or talk or think, a tiny, helpless version of everything you would one day become. The room is still, your eyelids are heavy, and somewhere in the Milky Way, right now, at this very moment, protostars are forming inside molecular clouds, disks are spinning, gas is falling inward, new solar systems are being born. The process that created you is happening again, right now, in real time, while you rest. In and out. As the protostar grew, the disk around it evolved in fascinating ways. The temperature of the disk varied enormously with distance from the center. Close to the protostar, where the gas was thick and the gravitational energy release was intense, temperatures soared to thousands of degrees, hot enough to vaporize everything. Metals, minerals, ice, all of it reduced to individual atoms and molecules swimming in a soup of superheated gas. Further out, the temperature dropped a few hundred degrees at the distance where the Earth would eventually orbit, a few tens of degrees where Jupiter's orbit would be, and at the outermost edges of the disk, temperatures were barely above absolute zero, cold enough for water to freeze, for methane to solidify, for ammonia to crystallize into tiny snowflakes drifting through the dark. This temperature gradient had profound consequences for the structure of our solar system. It determined what kind of material could exist in solid form at each distance from the Sun, and therefore what kind of planets could form there. Close to the protostar, only the most heat-resistant materials could remain solid. Metals like iron and nickel, minerals like silicates and oxides. These are the building blocks of the rocky planets: Mercury, Venus, Earth, Mars. Further out, beyond a boundary called the frost line or the snow line, water could freeze into ice, and ice is far more abundant in the cosmos than rock, because hydrogen and oxygen are far more common elements than iron and silicon. the frost line, there was simply much more solid material available to build things with, and the things that were built there were correspondingly larger. Jupiter, Saturn, Uranus, Neptune, the gas and ice giants of the outer solar system all formed beyond the frost line, where ice added enormously to the mass of solid material available for planet building. The frost line of our solar system was at roughly the distance of Jupiter's current orbit, about 5 times the distance from the Earth to the Sun. This is why the inner solar system has small rocky planets and the outer solar system has large gas and ice giants. The temperature gradient in the protoplanetary disk determined the architecture of our planetary system. Your body is warm, the room around you is cooler, and beyond the walls, the night air is cooler still, a temperature gradient, just like the one in the protoplanetary disk. You are the warm center, the protostar, and the world around you cools as the distance increases. In and out. Within the disk, the first solid objects were forming, tiny grains of dust, some inherited from the original molecular cloud, others condensing from the cooling gas as it moved away from the protostar. These grains were incredibly small, a few micrometers across, roughly the size of particles in cigarette smoke. But these tiny grains were not content to remain small. When 2 grains collided gently enough, they stuck together, held by weak electrostatic forces or by the stickiness of ice coatings on their surfaces, forming slightly larger clumps. These clumps collided with other clumps and stuck together too, forming even larger aggregates, fluffy, irregular structures that looked like cosmic dust bunnies, growing from micrometers to millimeters to centimeters to meters. This process is called accretion, and it is the fundamental mechanism by which planets are built, starting from grains smaller than the width of a human hair and ending with worlds thousands of kilometers across. It is a process of extraordinary patience, each collision adding a tiny amount of mass, each sticking event making the object very slightly larger, very slightly heavier, very slightly more gravitationally attractive to its neighbors. Patience is the theme of this story. Gravity is patient. Accretion is patient. The cloud was patient. The protostar is patient. And tonight, you can be patient too. Patient with yourself, patient with sleep, letting it come in its own time, the way planets come in their own time, grain by grain, atom by atom, in and out. Let us think a little more about the spinning of the disk, because it is one of the most beautiful aspects of this story, and it connects to something you can feel right now if you pay attention. You are lying on a planet that is spinning right now. The Earth rotates on its axis once every 23 hours and 56 minutes, carrying you around at a speed that depends on your latitude. At the equator, you are moving at about 1,670 kilometers per hour. Even at the poles, you are slowly turning, like a figure on a rotating music box. You cannot feel this rotation because everything around you is moving at the same speed, but it is there, and it has been there since the Earth first formed from the spinning disk. The spin of the Earth is a memory of the spin of the protoplanetary disk, which is a memory of the spin of the collapsing cloud, which is a memory of the random turbulent motions inside the original molecular cloud. Every time the Earth turns, it is echoing a rotation that began 4.6 billion years ago in a cloud of cold gas and dust, an ancient rhythm carried forward across the entire history of the solar system, unchanged in its direction, and only very slowly altered in its speed. When you lie in bed and feel the stillness of the night, you are actually spinning through space at tremendous speed, carried by a planet that remembers the original rotation of the cloud that made it. Stillness and motion, existing at the same time, the same way sleep and awareness can coexist at the edges of consciousness. In and out. The protoplanetary disk was not merely spinning, it was also evolving, changing its structure over time, driven by forces that competed and cooperated in intricate ways. The pillow holds your head, the mattress holds your body, and the laws of physics held the disk in a state of dynamic balance, not static, not frozen, but flowing, evolving, reshaping itself moment by moment, the way your thoughts reshape themselves as you drift towards sleep. In and out. As dust grains grew into larger objects, the process of planet building entered a new phase. Objects that had grown to about 1 kilometer across are called planetesimals, and at this size, gravity begins to play a significant role in their growth. A kilometer-wide body has enough mass to attract nearby smaller objects, pulling them in, accumulating mass more efficiently than the random sticky collisions that built the smaller grains. This is called gravitational focusing, and it dramatically accelerated the growth rate of the largest objects in the disk. The rich got richer. The biggest planetesimals grew fastest because they had the strongest gravity, attracting the most material, which made them bigger, which gave them stronger gravity, which attracted even more material. Within a few million years, some planetesimals had grown to hundreds of kilometers across, becoming what astronomers call planetary embryos, each one a miniature world with enough mass to have a spherical shape, perhaps even enough internal heat to be partially molten. And in the inner solar system, these planetary embryos began to collide, merging, growing, each collision adding mass and energy and reshaping the growing world. The Earth was built from these collisions, dozens of planetary embryos, each one roughly the size of the Moon or Mars, crashing together over tens of millions of years, melting and merging and cooling and solidifying, building up the mass of our planet layer by violent layer. It was not gentle, it was not quiet, but it was necessary. The violence of those collisions created the heat that melted the Earth's interior, allowing the iron to sink to the center and the lighter rock to float to the surface, creating the layered structure we have today. But that is a story for another night. Tonight, we are following the sun. The room is quiet around you. The violence of planet formation is 4.6 billion years in the past. The Earth has long since cooled, solidified, grown its oceans and its atmosphere and its continents, and you are resting on the stable result of all that ancient chaos, held by a planet that has had billions of years to settle down. In and out. While the planets were beginning to form in the disk, the protostar at the center continued to evolve. After about 100,000 years of rapid accretion, the infall of gas began to slow. The surrounding envelope of cloud material was thinning. Most of the original cloud had either fallen onto the protostar, settled into the disk, or been dispersed by the radiation and outflows from the growing star. The protostar was now entering a new phase of its life, the T Tauri phase, named after the first star of this type to be identified, T Tauri, in the constellation of Taurus, discovered in the 1940s. T Tauri stars are young, restless, volatile. They are protostars that have shed most of their surrounding envelopes, so they are visible for the first time in optical light. But they are not yet burning hydrogen through nuclear fusion. They are still powered primarily by gravitational contraction, the Kelvin-Helmholtz mechanism, slowly shrinking and heating up as gravity compresses them further. T Tauri stars are dramatic objects. They are significantly brighter than they will be as mature stars because they are larger and their surfaces are hotter than their final equilibrium state. Our Sun, as a T-Tauri star, was perhaps 2 to 3 times as luminous as it is today, despite being slightly cooler at the surface, because it was physically larger. They are also highly variable, their brightness changing unpredictably over days and weeks, as magnetic activity produces enormous star spots on their surfaces, as gas falls unevenly from the disk onto the star, and as flares erupt from their tangled magnetic fields. The young Sun was a turbulent adolescent, not yet the steady, reliable star it would become, but a wild, flickering presence, sometimes bright, sometimes dim, always restless. And from the poles of this young star, powerful jets of gas were streaming outward, bipolar outflows, twin beams of superheated material launched from the magnetic poles of the protostar at hundreds of kilometers per second, punching through the remnants of the surrounding cloud like spotlights piercing fog. These jets are one of the most visually stunning features of young stellar systems, and astronomers have photographed them around hundreds of protostars in nearby star-forming regions. Long, thin beams of glowing gas extending for light years in both directions, carrying away excess energy and angular momentum from the young star. Our Sun had jets like these long ago, before any of the planets had finished forming. The Sun was shooting beams of gas into the void, as if announcing its presence to the galaxy, saying, "I am here, I have arrived, I am becoming a star." The bed holds you, the room is still, and 4.6 billion years ago, the young Sun blazed and flickered and launched jets of gas into the darkness, a restless child, full of energy, not yet settled into the calm, steady burning that would sustain it for billions of years. In and out. Even the Sun had to learn how to be still. It took millions of years, but eventually, it found its equilibrium, its balance, its calm. And tonight, you are finding yours. The T-Tauri phase of the Sun's life lasted for roughly 10 to 30 million years, and during this time, the young star was slowly contracting, growing denser, growing hotter at its core, inching ever closer to the threshold of nuclear fusion. To understand what was happening inside the protostar during this phase, imagine squeezing a ball of clay in your hands. The harder you squeeze, the denser the center becomes, and the warmer it gets, because the energy of compression has nowhere to go but inward. The core of the protostar was being squeezed by the weight of all the gas above it, hundreds of thousands of Earth masses pressing down from all directions, compressing the hydrogen at the center to extraordinary densities and extraordinary temperatures. By the time the T-Tauri phase was well underway, the core temperature had risen to several million degrees, hot enough to strip electrons from atoms entirely, leaving nothing but a soup of bare atomic nuclei and free electrons, a state of matter called plasma. And the protons in this plasma, the bare hydrogen nuclei, were moving incredibly fast, colliding with each other millions of times per second, bouncing off each other's electromagnetic repulsion like tiny billiard balls, each one carrying an enormous amount of kinetic energy. But the electromagnetic repulsion between two protons is extremely strong. Both carry a positive charge, and like charges repel each other. The closer two protons get, the harder they push each other apart. To fuse two protons together, they need to get close enough for the strong nuclear force to take over, and the strong force has a very short range, less than a femtometer, 1/1,000,000th of a billionth of a meter. The protons need to be practically touching before the strong force can grab them and bind them together. At a few million degrees, the protons are fast, but not fast enough. They slam into each other at tremendous speeds but bounce off before they can get close enough for fusion. The electromagnetic repulsion is too strong. The barrier is too high. This is where quantum mechanics comes to the rescue with one of its strangest and most beautiful tricks. The room is dark and warm, your body is relaxed, and deep inside the story of the sun, we are approaching the most magical moment of all, the moment when quantum mechanics will allow the impossible to happen. In and out. In quantum mechanics, particles do not have definite positions. They exist as probability waves spread out over a region of space, and there is always a small but non-zero probability that a particle will be found somewhere it classically should not be able to reach. This is called quantum tunneling, and it means that a proton approaching another proton, even if it does not have quite enough energy to overcome the electromagnetic repulsion, has a tiny probability of appearing on the other side of the barrier, as if it tunneled through a wall. The probability is extremely small for any individual pair of protons, incredibly small. But inside the core of the protostar, there were an astronomical number of protons, colliding an astronomical number of times per second, and so even an incredibly small probability, multiplied by an incredibly large number of attempts, produced a steady rate of fusion reactions. This is how stars ignite, not with a sudden explosion, not with a dramatic flash, but through the slow accumulation of quantum mechanical improbabilities, each individual fusion event fantastically unlikely, but the sheer number of opportunities making it inevitable. It is like rolling a die with a billion faces and needing to roll a 1. If you roll it once, you almost certainly will not get a 1, but if you roll it a trillion times per second, you will get millions of 1s every second. The core of the protostar was rolling that die trillions of times every second, and every successful roll produced a tiny burst of energy, a photon of gamma radiation, a positron, a neutrino, each one carrying a small parcel of the energy that would one day warm your face and light your sky. In and out. Even the sun was born through patience and probability, through the accumulation of tiny, unlikely events, and perhaps there is a comfort in that. The most important things do not require certainty. They only require enough attempts. The first fusion reactions began when the core temperature reached approximately 10 million degrees, roughly 15 million degrees Celsius at the very center. At this temperature, the proton-proton chain reaction began to operate, the specific sequence of fusion events that converts hydrogen into helium inside stars like our Sun. The first step is the hardest. Two protons collide and tunnel through their mutual repulsion, and at the moment of contact, one of them undergoes a transformation, converting from a proton into a neutron through the weak nuclear force, while emitting a positron and a neutrino. The result is a deuterium nucleus, a single proton bound to a single neutron, the simplest compound nucleus that exists. This first step is agonizingly slow. Even inside the Sun, a given proton in the Sun's core will wait, on average, about 1 billion years before it successfully fuses with another proton to form deuterium. That is how rare the quantum tunneling event is. But the Sun's core contains an enormous number of protons, and so even though each individual proton waits 1 billion years, billions of fusions are happening every second across the core as a whole. The second step is much faster. The deuterium nucleus quickly fuses with another proton to form helium-3, a light isotope of helium. This reaction happens within seconds of the deuterium being formed. And the third step involves two helium-3 nuclei, colliding and fusing to form a single helium-4 nucleus, releasing 2 protons back into the plasma in the process. These protons are then free to start the cycle over again. The net result of this entire chain is that 4 protons are converted into 1 helium-4 nucleus, and in the process, a small amount of mass is lost, converted into pure energy according to Einstein's famous equation, E equals mc squared. The amount of mass lost in each reaction is tiny, less than 1% of the original mass of the 4 protons, but the speed of light squared is an enormous number, and so even a tiny amount of mass produces an extraordinary amount of energy. The Sun converts roughly 600 million tons of hydrogen into helium every second, and in the process, about 4 million tons of mass are converted directly into energy. That energy becomes the sunlight that warms the earth, the light that feeds the plants, the heat that drives the weather, the warmth on your skin on a summer afternoon. 4 million tons of the sun, vanishing every second, transformed into light and heat and neutrinos flowing outward through the solar system, warming everything it touches, including you. Your blanket is warm, your body is warm, and far away, a star is burning 4 million tons of itself every second to keep you that way. It has been doing this for 4.6 billion years, and it will continue for another 5 billion, patient and steady and generous beyond all measure. In and out. The moment of ignition was not a single dramatic instant. It was a gradual transition, like dawn, not a switch being flipped, but a slow brightening that took hundreds of thousands of years to complete. As the core temperature rose past 10 million degrees, the first fusion reactions began, tentatively, producing a small amount of energy, not yet enough to support the star against gravity, but enough to slow the contraction slightly. Over the following millennia, the fusion rate increased as the core continued to heat up, more protons finding each other, more quantum tunneling events succeeding, more energy being released. The protostar was learning to burn, finding its rhythm, like a heart learning to beat. Eventually, the energy produced by fusion balanced the energy lost from the surface, and the protostar stopped contracting. For the first time in its existence, it was self-sustaining. It no longer needed to draw on gravitational energy to keep itself hot. It had found an internal source of power that could last for billions of years. This is the moment when a protostar becomes a star, not with a flash or an explosion, but with a settling, a finding of balance, a reaching of hydrostatic equilibrium powered not by contraction but by fusion. The sun had ignited, our star was born, and the light it produced in that first moment of true stellar burning would travel outward through the disk, past the forming planets, past the icy rubble at the outer edges, and out into the galaxy, joining the light of hundreds of billions of other stars, adding one more point of brightness to the Milky Way. In and out, the sun found its balance, and you are finding yours. The star settled into its rhythm, and you are settling into yours. There is a kinship between you and the sun tonight. You are both finding rest, the sun in its long, slow burning, you in your sleep. The bed holds you, the room is dark and warm, and the sun burns on, as it has for 4.6 billion years, steady, reliable, patient, the most important star in your sky. But the story of the young sun did not end with ignition. There was still work to be done, a neighborhood to be cleared, a solar system to be shaped. During the T-Tauri phase, the young sun produced an extremely powerful solar wind, a stream of charged particles flowing outward from the stellar surface at hundreds of kilometers per second. This T-Tauri wind was far more intense than the solar wind the sun produces today, perhaps 100 times stronger, perhaps 1,000 times. It was a gale of protons and electrons and helium nuclei, blasting outward in all directions, sweeping through the inner solar system like a broom through a dusty room. The wind interacted with the remaining gas in the protoplanetary disk, pushing it, heating it, stripping it away from the inner regions. Over a few million years, the solar wind, combined with the intense ultraviolet radiation from the young sun, cleared the inner solar system of its remaining gas. This was a critical moment because until the gas was cleared, the newly forming rocky planets were in danger of accumulating thick hydrogen and helium atmospheres. If the gas had stayed, Earth might have ended up more like a small Neptune than the rocky world it became, with a thick, crushing atmosphere of hydrogen and helium rather than the thin nitrogen-oxygen atmosphere we breathe today. The T-Tauri wind saved us. It stripped the inner solar system of gas at just the right time, after the rocky planets had formed their solid cores, but before they could accumulate massive gaseous envelopes. Further out, beyond the frost line, the gas was too far from the sun for the wind to strip it away entirely, and this is where Jupiter and Saturn had already grown large enough to hold on to their enormous gaseous atmospheres. Their gravity was strong enough to resist the wind, to keep what they had gathered, to become the gas giants we see today. The difference between the inner and outer solar system, between the small rocky planets and the large gas giants, was shaped in part by the young sun's violent adolescence, its fierce wind clearing the inner regions while the outer planets held their ground. The air you breathe tonight, nitrogen and oxygen and argon, exists only because the T-Tauri wind cleared away the hydrogen and helium that would otherwise have made Earth's atmosphere unbreathable. Your lungs are a consequence of the sun's youthful fury, and every breath you take is a thank you to the young star that swept the sky clean. In and out, breathe in the atmosphere that the T-Tauri wind made possible, and breathe out the tension of the day. The T-Tauri phase also produced ultraviolet radiation intense enough to heat the surface layer of the protoplanetary disk, driving a slow evaporation of gas from the disk's surface, a process called photoevaporation. Imagine the disk as a pond and the sun's ultraviolet light as warm sunshine falling on the water's surface. Over time, the water evaporates, the pond shrinks, and eventually it dries up entirely. The protoplanetary disk underwent the same process. The gas evaporated from the top and bottom surfaces of the disk, blown away by the solar wind and ultraviolet radiation, and over a period of about 3 to 10 million years. The disk was gone, dispersed into space, leaving behind only the solid objects that had formed within it, the planets, the asteroids, the comets, the seeds of everything to come. With the disk gone, the young solar system was revealed for the first time, a yellow star at the center, still settling into its main sequence equilibrium, surrounded by a handful of rocky planets close in, a few gas giants farther out, and a scattering of smaller, icy bodies at the very edges. It did not look exactly like the solar system you know. The planets had not yet migrated to their current orbits. The asteroid belt was still being sculpted by Jupiter's gravity. The outer solar system was still chaotic and unsettled. But the sun was there, glowing steadily for the first time, and the fundamental architecture of our planetary system was in place. The room is quiet around you, the night outside is dark, and somewhere above the roof, the sun is on the other side of the Earth, shining on the other hemisphere, or waiting just below the horizon, ready to rise in a few hours and repeat what it has done every morning for 4.6 billion years. Shine, in and out. Let us now return to the gravity that started it all and think about it in a different way, the way you might return to a familiar room and notice details you missed the first time. Gravity is often described as a force, a pull between objects, and that is how Isaac Newton understood it in the 17th century. He showed that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. But in 1915, Albert Einstein replaced Newton's picture with something far more beautiful. He showed that gravity is not a force at all, it is the curvature of space-time. Mass tells space-time how to curve, and curved space-time tells mass how to move. Imagine a heavy ball placed on a stretched rubber sheet. The ball creates a dip in the sheet, a curvature, and if you roll a smaller ball across the sheet near the dip, the smaller ball will curve toward the larger one, not because there is a force pulling it, but because the surface it is rolling on is curved. This is what the molecular cloud experienced. The mass of the cloud curved the space-time around it, and the curvature guided the gas and dust to move inward, toward the center of mass, not because of a force pulling from the middle, but because the shape of space itself directed everything to converge. The birth of the sun was the geometry of the universe expressing itself, space curving under the weight of matter, and matter following the curves of space, a beautiful self-reinforcing dance between the content of the universe and its shape. You are lying on a planet that curves the space-time around it, and your body follows those curves, pressed gently into the mattress by the curvature of space created by 6 billion trillion tons of rock and iron beneath you. Gravity is not pulling you down. The Earth is curving the space around you, and you are following the curve, gently, naturally, the way water follows the contour of a hillside, the way sleep follows the contour of exhaustion, in and out. Let us think once more about the temperature rise at the center of the collapsing cloud, because it is worth revisiting with fresh metaphors. When the cloud began to collapse, the center was cold, barely 10 degrees above absolute zero, cold enough that the molecules moved sluggishly, barely vibrating, a frozen silence at the heart of a frozen cloud. As gas fell inward and compressed, the temperature rose, slowly at first, then faster. 10 degrees became 100, 100 became 1,000, 1,000 became 10,000. Each stage representing more energy concentrated in a smaller volume, more movement, more vibration, more heat. Think of it as a gathering of warmth, like the way a room warms when people enter it, each person adding their own small contribution of heat, and the room growing cozier and cozier as more arrive. The collapsing cloud was a room filling with warmth, atom by atom, molecule by molecule, the cosmic gathering of a party that would eventually produce a star. By the time the core reached 10 million degrees, the party was ready to begin. The guests had arrived, the energy was sufficient, and the first protons began to fuse. But that temperature did not arrive overnight. It took millions of years of patient compression, millions of years of gas falling inward, millions of years of gravity doing its slow, quiet work. Patience. The universe is extraordinarily patient. Gravity is patient. The laws of physics are patient. They do not rush. They do not worry. They simply operate consistently, reliably, for as long as it takes. And tonight, patience is what will carry you to sleep. Not effort, not trying, not forcing your eyes closed or commanding your mind to stop. Just patience, the willingness to wait, to let the warmth gather, to let the rest accumulate, until the threshold is crossed and sleep takes over the way fusion took over the protostar. In and out. Let us visit the spinning disk one more time, because we have not fully appreciated how remarkable it was. The protoplanetary disk extended from very close to the protostar, perhaps just a few million kilometers from its surface, all the way out to several hundred astronomical units. One astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. So the disk stretched from very near the center to perhaps 100 times the current distance from the Sun to Neptune, a truly enormous structure, thin as a razor blade relative to its width, like a DVD scaled up to the size of a solar system. At its thinnest, the disk was only a few % of its radius in thickness, which means that if the disk was scaled down to the size of a dinner plate, it would be thinner than a sheet of paper. And yet within that impossibly thin structure, all the ingredients for a solar system were present, all the matter that would become planets and moons and asteroids and comets, spinning together in a vast flat whirlpool. The disk was not smooth and featureless. It had structure, rings of varying density, gaps where the gravity of forming planets had swept out corridors of emptiness, spiral arms where gravitational instabilities created patterns in the gas, bright spots where planetesimals were colliding and growing. We know this because we can see disks like this around other young stars today. The ALMA telescope has revealed protoplanetary disks in exquisite detail, showing rings and gaps that almost certainly indicate planets forming within them. Each disk a solar system in the making, each one unique, each one telling its own version of the story we are hearing tonight. Some of these disks are only a few 100,000 years old, barely begun, still thick and massive, still actively feeding their young stars. Others are millions of years old, already thinning, already showing signs of planet formation, the gas beginning to dissipate, the solid bodies beginning to emerge. Each one is a nursery, a cradle, a place where gravity and chemistry and time are collaborating to produce something new, something that has never existed before. The room holds you like a cradle, the blanket tucks around you like a nursery, and somewhere in the galaxy, right now, a disk is spinning and a new world is being born. The story of creation is not a one-time event. It is happening all the time, everywhere, continuously. The universe never stops creating. In and out. Let us think about what the very young sun looked like once it had ignited and the disk was beginning to clear. The newly born sun was very similar to the sun we see today, but not identical. It was slightly cooler at the surface, perhaps 5,500 degrees Kelvin compared to today's 5,778 degrees. It was slightly less luminous, about 70% of its current brightness. This is called the faint young sun problem, and it has puzzled scientists for decades, because if the sun was 30% dimmer 4.6 billion years ago, then the Earth should have been much colder, cold enough for the oceans to freeze entirely, locked in a global ice age from which it might never have escaped. But we know that liquid water existed on the early Earth. We know this from ancient rocks, from sedimentary deposits that could only have formed in the presence of flowing water, from zircon crystals that carry chemical signatures of wet conditions at the Earth's surface as early as 4.4 billion years ago. So how was the early Earth warm enough for liquid water, despite the fainter sun? The answer almost certainly involves the greenhouse effect. The early Earth's atmosphere was rich in carbon dioxide and methane, both powerful greenhouse gases that trap heat and warm the surface far beyond what sunlight alone could provide. The faint young sun gave just enough light to warm the earth above freezing, thanks to the thick insulating blanket of greenhouse gases in the early atmosphere. It was a delicate balance, a collaboration between star and planet, each one contributing what it could, the sun providing light, the atmosphere trapping heat, and together they created conditions warm enough for oceans and eventually for life. Your blanket is a kind of greenhouse, trapping the heat your body produces, preventing it from escaping into the room, and keeping you warm even though the room itself may be cool. You are your own faint young sun, producing just enough warmth to sustain yourself, as long as you have a good enough blanket to hold it in and out. Let us now think about the sun as it is today, 4.6 billion years after its birth, a mature star, settled and steady, the anchor of our solar system. The sun is a nearly perfect sphere of hot plasma, about 1.4 million kilometers in diameter, roughly 109 times the diameter of the Earth. You could fit 1.3 million Earths inside the volume of the sun. Its surface temperature is about 5,778 degrees Kelvin, hot enough to glow with a warm yellow-white light, hot enough to vaporize any material that comes too close. But its core temperature is about 15 million degrees, more than 2,000 times hotter than the surface, compressed to a density about 150 times the density of water. This is where the fusion reactions take place, in a region roughly the size of the Earth, at the very center of the star. The sun has been burning hydrogen in its core for 4.6 billion years, and it has converted roughly half of the hydrogen in its core into helium. It has enough fuel remaining for approximately another 5 billion years of burning, which means it is roughly halfway through its life. A middle-aged star, steady and reliable, with billions of years of burning ahead of it. The sun's luminosity has been slowly increasing over its life. It is about 30% brighter now than it was when it was born. This brightening is caused by the gradual accumulation of helium in the core, which increases the mean molecular weight of the core material, requiring higher temperatures and pressures to maintain equilibrium, which in turn increases the rate of fusion. In another billion years or so, the sun will be about 10% brighter than it is today, which will significantly impact the climate on Earth, perhaps pushing the habitable zone outward, making Earth too warm for liquid water on the surface, while Mars grows warmer and more hospitable. But that is a billion years away, a span of time so vast that it dwarfs the entire history of complex life on Earth. You have nothing to worry about tonight. The sun is steady, the Earth is safe, and the stars are shining in and out. Let us think about one more thing before the story comes to its end. Something about the light of the sun that you may not have considered. The photons that the sun produces in its core take an extraordinary journey to reach you. As we mentioned earlier, they do not travel in a straight line from the core to the surface. They are absorbed and re-emitted countless times by the dense plasma of the sun's interior, zigzagging randomly, a journey that takes tens of thousands of years to complete. But here is the remarkable part. The photon that was produced in the core and the photon that eventually leaves the surface are not the same photon, not really. Each time a photon is absorbed by an atom in the sun's interior, it ceases to exist, and when the atom re-emits a photon, it creates a new one at a different wavelength, in a different direction. So the journey from core to surface is not one photon making a long trip. It is a relay race, millions of photons, each one living for only a fraction of a second before being absorbed and replaced by a new one. The energy is passed from photon to photon to photon, like a message being whispered from person to person in a long line. By the time the energy reaches the surface, it has been transformed. The gamma rays produced in the core have been broken down into millions of lower energy photons, visible light, infrared, the warm, gentle wavelengths that sustain life on Earth. The sunlight that touches your skin is not a single photon from the core. It is the final runner in a relay that has been passing the baton for 100,000 years. An ancient message of energy, filtered and softened and transformed by the sun itself, from the violent gamma rays of fusion to the gentle warmth of visible light. The sun takes its own ferocious energy and softens it, makes it gentle, makes it livable before sending it out into the world, a fierce nuclear furnace at the heart, but a warm, gentle glow at the surface. Violence transformed into tenderness by the patient work of 100,000 years of absorption and re-emission. There is something deeply moving about that. The sun's core is unimaginably violent, 15 million degrees, nuclear reactions releasing gamma rays, protons colliding at incredible speeds. But the light that actually reaches us is soft, warm, life-giving. The sun takes its own fury and turns it into something beautiful, something nurturing, something that grows flowers and warms oceans and lights the faces of children. And tonight, that transformed light is stored in the food you ate today. The energy that powers your heartbeat, the warmth in your muscles, the electricity in your neurons, all of it originally gamma rays from the sun's core, softened and transformed and passed along through 100,000 years of patient relay until it became the quiet energy that powers your rest. In and out, the energy rests inside you, the sun's gift, ancient and transformed and gentle. The room is very quiet now, the kind of quiet where you can hear your own heartbeat if you listen carefully, a soft, rhythmic thud, steady and reliable, powered by sunlight that left the sun's core 100,000 years ago and reached the Earth 8 minutes ago and entered your body through the food you ate today. Your heartbeat is a solar rhythm, one more expression of the energy that the sun has been sharing with the Earth for 4.6 billion years. Let it beat, slowly, steadily, the way the sun burns, the way the stars shine, the way gravity pulls, gentle and constant and sure. In and out, in and out. Good night. Let us return one last time to the molecular cloud, not to add new information, but simply to rest with the image, the way you would rest with a painting, not analyzing it, just letting it be beautiful. A vast dark cloud, cold and still, drifting through the Milky Way. Inside the cloud, hydrogen molecules barely moving, barely vibrating, barely aware of each other's presence, each one separated from its neighbors by enormous distances relative to its size. Dust grains, coated in frost, carrying the ashes of dead stars, drifting like snow through a windless night. And gravity, gentle, patient, persistent, pulling everything inward, slowly, quietly, with no voice and no urgency, just a steady, silent pull, like the pull of sleep on a tired body. That pull created the sun, and the sun created the conditions for everything else, and everything else eventually created you. You are the end product of a chain of events that began with a cold cloud of gas and was driven by the simplest force in nature, the gentle pull of gravity. Let gravity hold you tonight, not as a force pressing you down, but as a presence holding you close, the way the earth holds the moon, the way the sun holds the earth, the way the galaxy holds the sun, an embrace so gentle you cannot feel it, but so constant that it has never let go, not once, not in 4.6 billion years. In and out. Let us pause now and let the story breathe, the way you are breathing, slowly, gently, without hurry. Your body has been sinking deeper into rest for some time now. Your muscles have softened, your jaw has loosened. The small furrow between your eyebrows has smoothed. Feel the places where your body meets the bed, the backs of your heels, the curves of your calves, the broad flat weight of your lower back, the wings of your shoulder blades pressing gently into the mattress, the heaviness of your head on the pillow. At each of these points of contact, you are exchanging warmth with the material beneath you. Your body heat flows into the mattress, warming it, and the mattress absorbs that heat, holding it close, creating a cocoon of matched temperature around you. This is thermal equilibrium in miniature, the same process that drives the evolution of the entire universe, hot things cooling, cold things warming, until everything reaches the same temperature and the flow of heat stops. You are in thermal equilibrium with your bed, and that equilibrium feels like comfort, like safety, like rest. In and out. Let us trace the arc of the sun's birth one more time, gently, the way a lullaby returns to its chorus, not because you have forgotten the melody, but because the melody deserves to be heard again. A cloud of cold gas and dust, drifting through the Milky Way, ancient and dark and patient, made of hydrogen and helium and the ashes of dead stars. A supernova exploding somewhere nearby, sending a shock wave through the cloud, compressing it, nudging it past the tipping point. Gravity taking over, pulling the densest part of the cloud inward, slowly at first, then faster, a gathering, a drawing together, a collapse. The cloud spinning, faster and faster as it shrank, conservation of angular momentum turning a slow drift into a vigorous swirl. The cloud flattening, the sphere becoming a disk, a vast thin whirlpool of gas and dust with a growing hot core at its heart. The protostar, warming, compressing, glowing with infrared light, fed by gas spiraling inward through the disk, growing more massive with every passing century. The T-Tauri phase, adolescent fury, jets blasting from the poles, magnetic storms, flickering brightness, a restless youth still searching for stability. The core temperature rising, 10 million degrees, the proton-proton chain beginning, quantum tunneling making the impossible happen, fusion igniting, the sun's first true light. The T-Tauri wind sweeping the inner solar system clean of gas, the disk evaporating, the planets emerging, a new star and its family revealed for the first time. And then burning, steady, patient, reliable, for 4.6 billion years, warming the earth, lighting the sky, sustaining everything. That is the story, from cold dark cloud to warm bright star, from silence to light, from nothing in particular to everything you have ever known. In and out. The blanket holds your warmth, the room holds the quiet, and the sun holds the solar system together, its gravity anchoring every planet, every moon, every comet, every grain of dust in a slow, majestic dance that has been choreographed by physics and time. There is something deeply personal about the story of the sun's birth, because it is your story too. Every atom in your body was once part of the molecular cloud that gave birth to the sun. The hydrogen in the water that makes up 60% of your body mass was floating in that cloud 4.6 billion years ago, cold and dark and patient. The oxygen you breathe was forged in the core of a star that lived and died before our sun was born, scattered into space by a supernova, mixed into the molecular cloud, incorporated into the protoplanetary disk, and eventually delivered to the Earth by volcanism and cometary impacts. The iron in your blood was cooked in the last seconds of a massive star's life, in the silicon burning phase, the final day of fusion before the core collapsed and the star exploded. Iron atoms that traveled through the galaxy for millions of years before finding their way into the cloud that became our solar system. The calcium in your bones was produced in the explosive nucleosynthesis of a supernova, created in the fraction of a second when the shockwave ripped through the dying star, flinging newly minted atoms into the void. The phosphorus in your DNA, the element that forms the backbone of every gene in every cell of your body, was almost certainly made in a supernova or in the collision of two neutron stars, some of the most extreme events in the cosmos, producing one of the most essential elements for life. You are not merely on the Earth, you are of the Earth, and the Earth is of the Sun, and the Sun is of the cloud, and the cloud was of the galaxy, and the galaxy is of the universe. You are the universe, in a very literal sense, temporarily arranged in the shape of a person, lying in a bed, breathing air, listening to a story about where you came from. In and out, the stardust breathes, the stardust rests, the stardust dreams. Let that knowledge be a comfort tonight. You are made of the most ancient materials in the cosmos, materials that have survived supernovae and interstellar journeys and the formation of entire solar systems. Your atoms are durable. They will endure long after you have finished using them, passed along to other things, other beings, other stories. Nothing is ever truly lost. The first law of thermodynamics guarantees it. Energy is conserved. Matter is conserved. What exists will always exist, in one form or another, rearranged but never destroyed. The atoms that are you tonight will be something else tomorrow, and something else 1 billion years from now, and something else 1 trillion years after that. But they will always be. That is the gift of the molecular cloud, the gift of gravity, the gift of fusion, the gift of the sun, existence in all its forms, continuing forever. The bed holds you. The room is dark and warm. You are made of stars, and the stars are everywhere, above you, around you, inside you, and you can rest now, knowing that you belong to something vast and ancient and beautiful. In and out, in and out. Let us think about the sun in context, not as an isolated star, but as one among many. The sun was not born alone. Remember, our molecular cloud was part of a much larger cloud complex, and when the supernova shockwave triggered the collapse of our dense core, it almost certainly triggered collapses in many other dense cores nearby. The sun was born in a cluster, a group of perhaps 1,000 or several thousand stars, all forming at roughly the same time from the same parent cloud, sibling stars, born from the same material, in the same nursery. For the first few 100 million years of its life, the sun would have had neighbors, close neighbors, stars just a few light years away or less, all moving together through the galaxy as a loose group. But stellar clusters are fragile things. The gravitational interactions between the stars, combined with tidal forces from the galaxy itself, gradually pull the cluster apart. Over tens of millions of years, the siblings drift away from each other, scattered by the same gentle forces that once held them together. Today, the sun's birth siblings are scattered across the Milky Way. We do not know which stars they are, because the galaxy has had 4.6 billion years to shuffle them around. They could be anywhere. Some might be hundreds of light years away. Some might be on the other side of the galaxy. Astronomers have searched for the Sun's siblings, looking for stars with the same chemical composition, the same age, the same galactic orbit that might indicate a common origin. A few candidates have been identified, but none confirmed with certainty. There is something poignant about that. The Sun has siblings, but it has lost touch with all of them, separated by the slow drifting of the galaxy, each one now orbiting the Milky Way on its own path, warming its own planets, if it has any, shining its own light into the void. The pillow is soft, your body is warm and heavy, and the Sun orbits the center of the Milky Way at a speed of about 220 kilometers per second, carrying the entire solar system along with it. One complete orbit every 225 to 250 million years, a span of time so long that the Sun has completed only about 20 orbits since it was born. 20 trips around the galaxy in 4.6 billion years. The Sun is a slow and patient traveler. In and out, the Sun sits in one of the Milky Way's spiral arms, the Orion Arm, sometimes called the local spur, a modest structure between the larger Perseus Arm and the Sagittarius Arm. We are not at the center of the galaxy, not at the edge, not in a particularly special location. We are in an ordinary place, orbiting an ordinary star, in an ordinary arm of an ordinary spiral galaxy. And that ordinariness is itself extraordinary, because it tells us that the conditions for forming a habitable solar system are not rare or unusual. They can occur in ordinary places, with ordinary materials, given ordinary amounts of time. The universe does not need to be special to produce wonders. It only needs to be patient, and gravity does the rest. In and out. Let us now rest with one more idea, perhaps the most comforting idea of all. The Sun will not last forever. In about 5 billion years, it will exhaust the hydrogen in its core and begin to swell into a red giant, expanding until it engulfs the inner planets before shedding its outer layers and settling down as a white dwarf. But that is 5 billion years away. 5 billion years is an almost inconceivable span of time, longer than the current age of the Earth, longer than the entire history of complex life on our planet, long enough for evolution to produce countless new forms of life we cannot begin to imagine. Between now and then, the Sun will continue to burn with the same steady patience that has sustained it since it ignited in the heart of the collapsing cloud. Day after day, year after year, century after century, billion years after billion years. The Sun does not worry about the future. It does not fret about running out of fuel. It does not count the years remaining. It simply burns hydrogen into helium, 4 million tons per second, steady and generous and warm. There is a lesson in that for tonight. Do not count the hours until morning. Do not measure the minutes of sleep. Do not calculate or plan or worry. Simply rest, the way the Sun simply burns, without thought, without effort, following the laws of physics to their natural conclusion. In and out. The Sun knows nothing about itself. It has no awareness, no consciousness, no mind. It is simply matter and energy in a state of extraordinarily productive equilibrium, yet it sustains an entire solar system, and at least one world full of beings who think about it and wonder at it and tell stories about it on quiet nights. You are the part of the solar system that wonders, the part that looks back at the Sun and asks where it came from. The part that lies in bed at night and traces the story of creation from cloud to star to planet to person. And now you can let that wondering rest. You can set it down the way you set everything else down at the beginning of this journey, gently beside the door, knowing it will be there in the morning. The stars outside are shining. Some of them are young, still surrounded by the remnants of their birth clouds. Some of them are old, nearing the end of their fuel supply. Some of them are exactly like the sun, middle-aged, steady, burning hydrogen in their cores with the same quiet determination that has kept our sun going for 4.6 billion years. And all of them, every single one, was born from a cloud, touched by gravity, gathered by patience, and lit by the slow, impossible magic of quantum tunneling. The same story, told billions of times across the galaxy, each version slightly different, but all of them beautiful. And one of those versions is yours. The room is dark, the bed is warm, your eyes are closed, your breathing is slow. In and out, in and out, in and out. Good night, traveler, sleep well, and dream of clouds and dust and the slow, patient birth of light. There are some things about the newborn solar system that are worth knowing, even at the very edge of sleep, details that float past gently, and whether you catch them or not does not matter at all. The protoplanetary disk did not disappear all at once. It faded in stages. The inner regions cleared first, swept clean by the T-Tauri wind and ultraviolet radiation within a few million years. The outer regions lasted longer, perhaps 10 million years or more, before the last traces of gas dissipated. As the gas faded, the solid objects left behind began to interact with each other more directly. Without the cushioning effect of the surrounding gas, collisions between planetesimals became more energetic, more decisive. Objects either merged or shattered, depending on the speed and angle of impact. This was the era of giant impacts, a chaotic time when the inner solar system was littered with debris and the orbits of the forming planets were still being sorted out by gravitational interactions. It was during this era that the Earth reached something close to its final mass, growing from a collection of planetary embryos into a single large world through a series of massive collisions, each one adding material, each one releasing enough energy to melt the surface partially or completely. The early Earth was a world of molten rock, a magma ocean covering the entire surface, glowing red and orange under a thick atmosphere of steam and carbon dioxide, a hellish landscape by any human standard, but a necessary stage in the building of the planet you now call home. Over tens of millions of years, the surface cooled, the magma solidified into the first crust, the steam in the atmosphere condensed and fell as rain, enormous downpours that lasted for millions of years, filling the basins of the surface with water, creating the first oceans. The sun looked down on all of this, steady and warm, providing the energy that drove the cooling and the condensation and the chemistry that would eventually lead to life. The room is quiet. Your body has released its last hold on tension. Your breathing is barely perceptible, a gentle rise and fall, like the surface of a calm ocean, rising and falling with the tide, in and out. There is a beautiful symmetry to this story. It begins with cold and ends with warmth. It begins with darkness and ends with light. It begins with stillness and ends with burning. It begins with nothing in particular and ends with everything. And tonight, your own story follows a similar arc, in reverse. You begin warm and active and awake, and over the course of this journey, you have been cooling, settling, dimming, growing quieter, approaching your own kind of stillness. But unlike the heat death of the universe, your stillness is temporary. Tomorrow you will warm up again. Tomorrow you will rise. Tomorrow the light will return. The sun will be there waiting for you, as it has waited for every person who has ever woken on this planet, shining with the same light it has shone for 4.6 billion years. And you will open your eyes and feel its warmth and know that you are part of its story and it is part of yours, and that the bond between you and the sun is written in the atoms of your body, in the chemistry of your blood, in the oxygen in your lungs, in every photon that has ever touched your skin. You are a child of the sun, born from the same cloud, warmed by the same fire, carried through the galaxy on the same slow orbit, and resting tonight as the sun continues to burn, patient and steady and warm, for you and for everyone, in and out. The sun was born from a cloud, and the cloud was born from the galaxy, and the galaxy was born from the universe, and the universe was born from a mystery that physics is still working to understand. But tonight, the mystery can wait. The physics can wait. The questions can wait. Nothing needs to be solved tonight. Nothing needs to be understood tonight. You only need to rest. The way the cloud rested before it collapsed. The way the dust rested on the surfaces of ice grains in the dark. The way the protostar rested in its equilibrium of gravity and pressure. The way the sun rests now in its long, slow burning, neither growing nor shrinking, neither brightening nor dimming, simply being. Rest and let the cosmos carry you gently, deeply, all the way down into sleep, in and out, in and out, in and out. And now let us drift toward the close of our journey slowly, the way the protoplanetary disk slowly faded, revealing the young solar system for the first time. The story we have told tonight spans roughly 100 million years, from the first compression of the molecular cloud to the moment the sun ignited and the disk began to clear. 100 million years of patient gathering, of gravity doing its quiet work, of temperature rising and matter spinning and chemistry unfolding, and then 4.5 billion more years of steady burning, of warming the earth, of driving the weather and the tides and the seasons, of providing the energy that every living thing on this planet ultimately depends upon. The sun is the source, the origin, the beginning of the chain that leads to you, lying here tonight, warm and safe and held by a planet that orbits a star that was born from a cloud that was touched by a supernova that was triggered by the death of a star that was born from an even older cloud. Cycles within cycles, generations of stars giving birth to new generations, each one enriching the galaxy with heavier elements, each one leaving behind the raw materials for the next. Our sun is at least a third-generation star made from material that has been through 2 or more previous stellar lifetimes, recycled, refined, enriched with the heavy elements that make rocky planets and liquid water and living things possible. Without those earlier generations of stars, the molecular cloud would have been pure hydrogen and helium, and hydrogen and helium alone cannot make planets or people. They can only make stars. The heavy elements, the carbon and oxygen and iron and silicon, were added by the supernovae that preceded us, gifts from the dead to the living, from the past to the future. In and out, the universe gives and gives and gives generously, endlessly, across billions of years, and you are one of the things it has given, a temporary but magnificent arrangement of of its oldest materials. The night is deep now. The story is nearly told. Let your breathing become very slow, so slow you barely notice it. Let each breath take a long time to arrive and a long time to leave, like the long, slow infall of gas in the collapsing cloud, patient, unhurried, finding its own pace. Let your thoughts thin out, like the gas thinning at the edges of the protoplanetary disk, fewer and fewer, lighter and lighter, until there is almost nothing left but the quiet. The sun was born from darkness, and it brought light. You were born from a long chain of improbable events, and you brought consciousness. Both are remarkable, both are temporary, both are precious. And tonight, both can rest. The sun rests in its equilibrium, burning steadily, neither expanding nor contracting, neither brightening nor dimming, held in perfect balance between the outward push of fusion and the inward pull of gravity. And you rest in your own equilibrium, the weight of your body matched by the support of the mattress, the pull of sleep matched by the fading thread of awareness, a balance that will tip soon, gently, in the direction of dreams, in and out. Think one last time about the sun, not as a scientific object, not as a ball of plasma undergoing nuclear fusion, but as a companion, a presence, a source of warmth that has never failed you, not once, not in your entire life. Every morning it rises, every evening it sets, and through the night it shines on the other side of the world, warming other people, lighting other skies, and in a few hours it will return to you, as it has returned every morning since you were born. The sun is the most reliable thing in your life, more reliable than any person, any institution, any promise. It has been burning for 4.6 billion years, and it will burn for 5 billion more, and it asks nothing of you in return. It simply shines. That is what stars do. They give their light away, freely, in all directions, without preference or condition, to everything and everyone within their reach, a generosity so vast and so constant that we barely notice it. But tonight you can notice it, you can appreciate it, you can rest in the knowledge that you are cared for by a star, held by a planet, warmed by a fusion reactor 150 million kilometers away that has been running without interruption since before the Earth had oceans. The room is quiet, the air is still, the night is deep, and somewhere above or below or beside you, the sun is shining as it always has, as it always will, for billions of years to come. In and out. Let the last thoughts settle like the last grains of dust settling in the protoplanetary disk, slowly finding their places and then going still. The cloud collapsed, and the sun was born. The disk spun, and the planets emerged. The sun ignited, and the solar system was lit. Sleep well, traveler. Sleep the way the molecular cloud rested before its collapse, still and cold and patient. Sleep the way the protostar glowed, warm and growing and quiet. Sleep the way the sun burns, steady and generous and reliable. And dream, if you dream at all, of spinning disks and ancient clouds and the slow gathering of warmth at the heart of a star. In and out, in and out, in and out. The stars burn on above you, around you, inside you. The room is still, the night is gentle, and now the stars begin to dim behind your thoughts. You are a part of this cosmos, The carbon in your body was forged in the hearts of ancient stars. I hope you sleep well and dream softly. Good night.